yeah, the idea for today would be to talk a little bit about electromagnetic coupling. And we will probably not cover the whole chapter and section here, but at least think about the general principle and maybe some countermeasures and talk about plane wave fields. So that's the idea. So remember what we had before. Before we had conductive coupling over cables, and we had capacitive coupling that happened over electric fields, and we had inductive coupling that happened over magnetic fields. And all this, or this description would only work if our system is electrically small. If it's much smaller than a wavelength, or if we are, let's say, at low frequencies. At low frequencies, signals have large wavelengths. And so then this easy description would somehow work. We can say, we can put the whole coupling into one coupling capacitor, in one parasitic capacitance, or in one mutual inductance that somehow couples circuits with each other. And if we go to higher frequencies, if we go to smaller wavelengths, if our system dimensions gets larger in comparison with the wavelengths, then this does not work as nicely anymore. And so at higher frequencies, we also don't really have this pure magnetic field anymore or pure electric field anymore, right? An electric field you have if you have high voltages somewhere, and a magnetic field you get if you have high currents somewhere. And if you have power systems, of course, you have current and voltage at the same time. Yeah, but let's say if we would have a tram line, near a tram line, would you expect more electric coupling or more magnetic coupling?
Are the tram line in AC?
No, the tram lines are typically not AC. It's more like it's a direct current, and it's a direct or it's a more or less constant voltage, but the voltage level of a tram line is around 600 volts, and the current is around 1 kiloampere. So, yeah, the current is much stronger, let's say, than the voltage, because you don't want to have such high voltages for security reasons. So, yeah, near a tram line, you have more magnetic coupling. And now we could say, okay, but wait, it's a direct current. Why do we have magnetic coupling? If the magnetic field does not change because it's a direct current, why do we get then coupling and problems? Because the tram line accelerates and stops, and it does not consume the same current all the time. But for the drive wire, the catenary of a tram line, you have current and voltage. So you could have capacitive and inductive coupling, but the inductive coupling is more severe. And it's usually also sometimes, there is some AC component there, because of course you generate the current with some rectifier from AC, and it's a 3-phase rectifier. So 6 pulse rectifier. So you get 6 times 50 hertz. So you get 300 hertz, a 300 hertz component in this DC voltage of the tram line. And so let's say if you have some overhead lines somewhere, there's of course also high current there, but there's usually much higher voltage. We have 220 kilovolts, let's say. So there's also a quite intensive electric coupling. But it depends. And it depends on then also how fast does the voltage change? How fast does the current change? And sometimes even with a very small current, you can have a high magnetic coupling if the current changes rapidly. Sometimes even with very small voltages, you can have a strong electric field coupling if the voltage change is very strong, if the voltage changes rapidly. Okay, so, but if we go for higher frequencies, yes, and so for small wavelengths for electrically large systems, this does not work anymore, because you don't have a pure electric field, you don't have a pure magnetic field, And there's a nice talk from a German colleague of mine, Andreas Barchanski, who's working for CST, Computer Simulation Technology, in Darmstadt. And you can also search for this on, or we can, I won't do it now. Here's a nice talk that is called ENH, the electric and the magnetic field component. They are instant best friends forever. Because really in electromagnetics, you cannot have an electric field without a magnetic field and vice versa. And this is really what happens at these radio frequency fields. So electric and magnetic field are coupled to each other. They are not independent of each other. And what we did before, some approximation with this stationary, quasi-stationary fields, this does not work anymore. And so, as we discussed before, for what happens if systems gets nonlinear, it gets complicated from a mathematical point of view, and the same is what we have here. So if we take into account electric field and magnetic field at the same time, and if they depend on time, and if they also depend on the place, on the position along our system, so then it gets really complicated. Because we need to solve, remember what we did in the exercise, I don't know, 2 weeks ago when we solved this filter with solving the differential equation. Yeah, there we had a differential equation for charging the capacitor over the resistor that would just depend on time. Still, it was quite complicated to solve this differential equation. So here we would have differential equations that do not depend only on time, but also on position. And so the solution of this will be wave fields, how fields propagate through space. And yeah, so you can calculate and try to simulate this, but it's rather hard from a mathematical point of view. And then we have a further difficulty for closed or enclosed systems like a car body, like some aircraft fuselage, like maybe a ship hull, because they are made out of metal, and metal acts like a mirror for these electromagnetic waves. So if you have, or in a satellite body, or in a large industrial facility, if you have lots of metal around, then you generate some waves, they propagate through space, and then there will be reflected. And there might be re-reflected, and then you have these waves coming from one direction and waves coming from the opposite direction, and they will interfere with each other. And of course, there can be positive interference and there can be negative interference, and so on. And so these metallic enclosures, they then act like a cavity resonator, and due to this positive and negative interference, we can get strong field enhancements at certain frequencies. And at other frequencies, there will be almost no field because they will cancel each other. Okay. And so, now things are really getting complicated. So we need to have some approaches for approximation, let's say, right? At the end, we still want to have some good rules of thumb or some calculations, some formulas that we could still insert into a plain calculator and do something. And so the first idea for approximation is plane waves. Approximate our field by plane waves. This is what we will probably talk about today. So then another simplification is to look at the field of elementary dipoles, so simple dipole antennas. And there's some electric dipole that is also called Hertzian dipole after Heinrich Hertz, German physicist. And there's a magnetic dipole, so a loop antenna that is named after FitzGerald, I think some British physicist or maybe American, I'm not sure. And so the idea of them is they are not very physical, or they are not very practical if you would try to build them. At least the electric dipole, the magnetic dipole is better or is easier to build. But the advantage, the idea of them is that the mathematical description is not too complicated. Still, they give you very valuable results. That's the idea of them. And so if you have understood about them, you can also understand about more complicated antennas that would not be so easy to solve from a mathematical point of view, or where you could not so easily write down these equations. That's the idea of them. And so if we've understood about them, then we can go to more, to other types of antennas. And from an EMC point of view, the worst case is this half wavelength radiator or half wavelength antenna, a dipole antenna that is half a wavelength long, because this has the worst coupling. Okay, and so the result of all these analyses here is still at the end equations that you could use with your plain calculator, and that you could at least put into MATLAB and do something there. And yeah, still it would be a real challenge to include in this analysis additional metallic surfaces, like your car body, your aircraft fuselage, your ship, whatever. So if you want to do more exact analysis, you need to do numerical simulations. And there is quite a lot of software for this available, and there are different numerical methods that can be used, and you could cover a whole course of studies, let's say a whole master degree, just with numerical field simulation, or at least a couple of lectures, no problem, to talk in detail about these numerical field simulations. To name a few, this concept is something that has been developed by some German universities. So maybe let's switch to my browser, and maybe I have a search field here. So ENH, we can try to find this instant best friends. This is the video that I have mentioned on YouTube. So let's see if we find this there from Andreas Barchanski, ENH, Instant Best Friends Forever. Very nice talk, very interesting. So I recommend to take a look at this. And so then this concept 2. Okay, this is the website here. You can see some pictures of this tool, or of this family of tools, and this is a nice field solver to do such kind of analysis. I think they also have a website in English. Unfortunately, it's somehow discontinued, so it's not developed any further, unfortunately, which is a real pity from my point of view. So this FECO is something that has already also been started in Germany, is now a commercial product. I think it's developed in South Africa, because paying programmers there is cheaper than in Europe. And it's some abbreviation for field calculation of bodies with arbitrary surface shapes, something like this. So it's some abbreviation for what I just said, but in German. And it's now a commercial product. I think you need to have a license. It's still a very powerful tool. And this NEC is also kind of interesting. It stands for Numerical Electromagnetic Code. And you can, for example, find it on this website here. So there's also some examples, like a logarithmic periodic dipole antenna, and then some calculated radiation pattern of this. And this is a software that is now mainly used by amateur radio people to develop antennas and to calculate radiation and scattering of objects. And the nice thing about this is that it's very old. So it has been developed, I think, back in the 1970s, maybe even late 1960s during the Cold War, because one threat is maybe also something unfortunately that we have in recent days once again is you take an atomic bomb and you let the atomic bomb explode somewhere in the outer atmosphere. So the damage by heat and by pressure and so on will be very limited, but there is also a very high, strong electromagnetic pulse. And this electromagnetic pulse, of course, can be very severe to electronic infrastructure. So you can potentially destroy lots of infrastructure in the surrounding without doing too much harm. And of course, researchers, even at this time, have been interested in simulating what will be the impact to cables, to overhead lines, to antennas, and so on from these high altitude electromagnetic pulses. And for this purpose, this software has been developed. It was long time classified. But yeah, since the end of the Cold War, let's say, it's more or less open source and you can use it. And yeah, what's interesting from my point of view is, I'm not sure if we take a look at the tutorials. I'm looking for the handbook. So maybe support files. This is some beginner's guide. Here's the manual. And this website is obviously not updated anymore. Okay, then unfortunately I cannot show this. But what is quite funny is if you would check the original NEC manual, it's something that has been written on a typewriter machine, right? Because at this time computers were not that powerful, so computers were used to do calculations but not to write documents. So it's written on a typewriter machine, and then you scroll through this and you see some example that they say, oh, we do some electromagnetic field coupling, pulse coupling to some airplane. And you think, oh, how did they do this in the 1970s? Computers weren't that powerful, that didn't have so much memory and computational power. How did they analyze electromagnetic field coupling to an airplane? And so let me open up my drawing program. So, and then unfortunately the file is not available there anymore. Then you check this manual, how this airplane looks like. And the airplane looks like this. It's one wire for the main fuselage, and it's two wires for the wings, and two shorter wires for, let's say, the rear steering thing of the aircraft. And you say, okay, it's an aircraft. And the interesting thing is that still with this very simple model, I mean, what happens there is you get some electromagnetic wave. So we have some K vector and you have some electric field component, and you will also have a magnetic field component. Yeah, and so they will somehow impinge on this aircraft and excite this. And what will happen is you will get currents flowing along the aircraft. And the problem is if you excite resonances of this aircraft, if you get standing waves along this aircraft. So if you get something where you, let's say, have a minimum, because at the end of these wires and at the end of the aircraft, the current needs to be zero. Yeah. So if you get some standing wave, let's say, for example, from here to here, or from here to there, or from here to the front, and so on. And so for the rough approximation of these, let's say, first 3, 4, 5 resonant modes of this aircraft, this very simple model is totally sufficient. And you don't need to model all the details and the door and the windows and so on and so on. And so this is also, from my point of view, a problem nowadays, that computers are powerful enough that you can put, as we've seen on the website here of the concept, that you can put very complicated models. I think they also had a picture somewhere of an aircraft. So for example, here's a very detailed aircraft and surface currents on this aircraft. I think this is a computer case that we had just seen. And there was a full ship somewhere that has been modeled. So yeah, you can put all the details in the simulators nowadays, but at the end, of course, you get more information. But as a first starting point, very simple models are very useful. And as Edward Pelham-Box said, all models are wrong, some are useful. So don't, if you ever do such simulations, don't use too complicated models. And then all these softwares here, they are based on method of moments, and this is some numerical method then to solve Maxwell's equations. And the advantage here, for example, is that you only need to discretize and mesh all your conducting surfaces. You don't need to mesh the whole body, the whole structure, just the surfaces, which is, kind of efficient. And then the other softwares, CST, this is the one, as said, where Andreas Barchanski works for. This is also a company from Germany that also belongs to Dassault, which is a French company. And they use a different method, finite integration technique. And so all these methods, they have advantages and disadvantages. And if you ever do numerical field simulations for some EMC problems, the first thing to think about is what would be a good method for your problem. And so if you ask the manufacturers, they will all tell you, we can solve all problems, but they can't really. And so it's often the first thing that you need to decide what would be a good method to try to solve this problem. And the issue is, if you have just learned about one software and maybe about one method in your studies, then you are trying to use this method for each and every problem, even if it's maybe not that useful, right? It's the old saying, if you only have a hammer, everything else looks like a nail. And even if it's a screw, then you try to use the hammer to fix the screw instead of using a screwdriver. Okay, so then, we have this electromagnetic coupling, but what can we do against this? And some general countermeasure would be to use a compact design. So make systems smaller, decrease the length of cables, use symmetrical signal tracing, and bond everything together with ground straps that are shorter than, let's say, a tenth of the wavelength of the highest frequency of your interest. So, of course, sometimes your systems need to be large. You cannot make them smaller. Anyway, what you can do to lower the electromagnetic field coupling is you can try to shield the source, or you could try to shield the sink. So here's my cell phone. Cell phone also creates electromagnetic field problems, but could I shield the cell phone? Not really, because then it won't work anymore. So there are useful antennas in there. Of course, I can try to shield, let's say, the power electronic part in here from other modules. And if you would take a cell phone apart, we will talk about this if I try to get out of the full screen mode here. So, in the countermeasure section, there will be a whole topic and chapter devoted to shielding. We will think about this there in more detail. So you can try to shield something, but if you have useful antennas, you cannot shield the useful antenna. Okay, and so another idea, and this is also, as you have seen before, what we will talk about later on is filtering. You can try to filter cables, or you can try to filter unwanted signals on cables and so on. And then especially the common mode current, because this is the as we discussed before, this is the bad current that will strongly radiate. Okay. And if you have, for example, a shielded enclosure, and even if your cables are properly shielded and so on, then it's usually not a good idea, let's say, to have a shielded enclosure. Like maybe this one here, and you have one current going in on one side and current going out on the outside, because if you have some disturbance current flowing on the shield, or let's say if you have some mode conversion here on this side, then you will also have a current flowing on the whole surface, and your whole surface, even if it's somehow shielded, will act as an antenna. So usually you also don't want to have high frequency, radio frequency currents on your shield casing. Yeah. So, but as said, things are getting complicated here. So then we can have a more detailed look onto these electromagnetic fields. And as already said, the electric field component and the magnetic field component are instant best friends forever. They cannot be separated anymore. And our field will propagate, and we now get a field strength for the electric and magnetic field that does not just depend on time, but also on space. And this will lead us to much more complicated differential equations. So still, some values are simple and are useful. So at first, we will, if waves propagate, if signals propagate, they have some speed of or velocity of propagation. And this is the velocity of light, right? And so on cables, it will be a little less because we have this permittivity on the cable of the insulation of the dielectric. So there usually you have something like half of the wavelengths, 2/3 of the wavelength, something of the velocity in vacuum, something like this. And so if E and H, if we write them down as vectors, the cross product between them is called Poynting vector and is denoted with S, and S is the power flux density. And so this is a little bit like in, what is the unit of the electric field? It's volt per meter. And the unit of the magnetic field strength? So this is volt per meter. What? Yeah, current. So this is ampere per meter. And electric and magnetic field strength is what we discussed before. With capacitance and inductance are dual quantities. We can interchange current and voltage. We can interchange volt and ampere, and it's the same here. So this is in volt per meter. This is in ampere per meter. So if we have the product of the two, it's volt ampere per meter squared. So volt ampere is the same as watt. So this Poynting vector, this power flux density, that's why it's called power flux density, has the unit of watt per square meter, which perfectly makes sense. And so this equation here is the same as power is voltage times current for, let's say, DC circuits or for AC circuits or for usual circuits. You can have a very high voltage. If you have no current, you will have no power. You can have a very high current. If you have no voltage, you won't have power. And so it's the same here. You can have a very high electric field. If you have no magnetic field at the same time, at the same place, you won't have power, and so on. So yeah, think about this analogon to usual circuits that you might already know. Okay, and so then the easiest way to approximate fields is to use this plane wave approximation. So for this, unfortunately, I cannot go too far away because my microphone isn't working. But yeah, so I will switch to full screen mode for a second. So let's say this is an antenna. This is something that radiates because we might have a current flowing in this direction. We have a source in the center that generates a voltage. So this will have a positive voltage. This will have a negative voltage. And we are building up a charge here, a positive charge and a negative charge. So therefore we have a current flowing in this direction. And then we change the voltage, we change the charge, we change the current. So we have a positive and negative current and so on going in this direction. So if we have a current like this, we also get a magnetic field that will go in circles around this. And if the current changes, then the magnetic field that goes in circles around this will also change. So sometimes it will be positive, sometimes it will be negative. So now we get a changing magnetic field. So if we get a changing magnetic field, now you would need to look into Maxwell's equations. Once again, we get a changing electric field that also goes in circles around us. So this is now my changing magnetic field, right? That points to you and that points to me. And now once again with the right-hand rule, I get a changing electric field around this that now goes in circles like this. And so, okay, now you can have a look here. Now I get a changing electric field up and down. And if I have a changing electric field up and down, I get once again a changing magnetic field that does circles like this. And this magnetic field will once again create an electric field, and this will create a magnetic field, and we have wave propagation. We have a wave that propagates through space because each changing electric field will change a magnetic field, each changing magnetic field will change an electric field, and so on and so on. And so now we have a wave, or we have a field that propagates away from this source, from my antenna here. And so if we are close to the source, so if we are very close to the source, we have probably more of this electric field, because it's an electric dipole than magnetic field. But if we go away from the source, we have the same energy into the electric and magnetic field. And the wave fronts, so the places where the wave has, let's say, the same phase, are spheres. We get spherical waves. And so now I put the antenna some distance away. So the antenna is now there. I think I need to go to the other side. Yeah, so my antenna is now over there, quite a distance away. And so if I'm now away from the antenna, and if I would have a look at the waves here, the wave fronts are still spherical. But the curvature is very large already. So if my antenna would be even further away, then the wave front does not look too spherical anymore. It would almost be plane. The wave front would not be spherical anymore. It would be a plane, especially if I just look at the very small portion of this wave. And of course, the field strength over there is very large. But if I go away from the source, what happens to the field strength? It should become smaller. Because if I go back to my slides here, if we go back to this here, we see this is power flux density. This is the power that is radiated by my antenna divided by the area of this wavefront. And as said, the wavefront or the wavefronts are spheres. And there's a constant power radiated by the source. And if I go away from the source, the sphere would get larger, right? And so the radius of the sphere is the distance to the source. And how can you calculate, or how does the area, the surface area of a sphere depend on the radius of the sphere? So, of course, the larger the radius, the larger will be the surface area of the sphere, but with which exponent? And I've seen that I'm still not showing the full screen. So I refer to this equation here, right? We have electric field, magnetic field, and we have this power flux density, and this is power divided by area. Power stays constant, and area, if we go away from the source, grows larger. But how does it grow larger? If I double the distance, what happens to the area? If I double the radius of the sphere, what will happen to the surface area of the sphere? It will be squared. Yeah, so this depends on distance squared. And if we double the distance, we will have 4 times the surface area. So we will have only a fourth of the power flux density. So if we double the distance, this goes down by a factor of 4. But this will only go down by a factor of 2. This will also only go down by a factor of 2. So if we double the distance, we have a fourth of the power flux density, but we have half of the wavelength, half of the field strength, half of the electric field strength, half of the magnetic field strength. And so, yeah, if I go away from the source, so as said, the field strength will be very high. But if I go away from the source, field strength will go down with 1 over the distance. And 1 over the distance is some hyperbole. I don't know how to call it in English, but you know, it's a function that goes down like this. And so once again, if I'm quite a distance away from the source, now I could try to draw it in my drawing program here. So, if this is where our source is, and if we have the field strength, which is proportional to 1 over R, and this is R, then field strength goes down like this, right? This is how such a function looks like. And so now once again, if I'm quite away in quite some distance from the source and just look at a small portion, then the field strength almost does not change anymore. It almost stays constant with the distance. And so this is what we then also use in this plane wave approximation. So we are in the far field, we are quite in a distance from the source, we approximate the spherical wave front as a plane wave, and we assume the field to be homogeneous, and homogeneous means it does not depend on the position anymore. And so then our electric field, magnetic field, and this pointing vector, this power flux density, they are perpendicular to each other. And electric and magnetic field components have the same phase, because otherwise we would not have energy inside this wave. And there's a certain ratio between these field components. And so, yeah, once again, the unit of the electric field is or was volt per meter. The unit of the magnetic field strength is ampere per meter. So if you calculate the ratio and simplify it, yeah, the meters will cancel. You get volt by ampere, and volt by ampere is the same as ohm. And so that's why this ratio, it's not really an impedance, but it has the unit of some impedance. And that's why it's called wave impedance. And it's if we take the values of mu and epsilon in vacuum in air, it's called free space wave impedance. And it's approximately 377 ohm. Okay. Yeah. And so this is what we just discussed, Maxwell's equations there. So I won't go into this any detail. This is James Clerk Maxwell, the Scottish physicist and engineer that found about this and wrote them down the first time. And this is now the mathematical description how we could write down these plane waves. But in general, we have a constant amplitude. We have some components into the Cartesian directions, x, y, and z. And then we have some complex exponential function that gives us the propagation. And inside there is k. K is this wave vector that I've just drawn before here on my schematic. So this is, of course, also a vector. Okay, and so if you know the electric field, you can also write down the magnetic field. But as said, they are just perpendicular to each other. And this is all written in frequency domain. If you want to go back into time domain, you do inverse Fourier transform and you get waves that depend on angular frequency, time, and k and r as wave vector and spatial position in place. And I think some linearly polarized wave, where you can see the blue thing is the electric field, the green thing is the magnetic field. They are perpendicular to each other, and they propagate also in a direction that is perpendicular to each of them. So this is a linearly polarized wave. And now, as this is one solution of Maxwell's equation, you could superpose this. I think there's also another nice 3D approximation like this, some video that I found somewhere on the internet, it's the same thing, right? E and H are perpendicular and propagating in the transverse direction. That's why this is also called a transverse electromagnetic wave, some TEM wave. And now the idea is, if you, let's shortly go back to this one here. So if you have one of these waves that is linearly polarized, and if you add a second wave that is shifted by 90 degrees, and so spatially shifted by 90 degrees and also phase shifted by 90 degrees, then you get something like this that looks like this. So this is a circular polarized wave. And as you can see, still for each point, E and H are perpendicular to each other, and they are still perpendicular to the direction of propagation. And yeah, this would be called a right turning circular polarized wave. Do you have any idea where something like this is used? So, for example, if you have a weather balloon, and if you want to transmit data from and to the weather balloon might rotate. And so if you have a linearly polarized antenna, like this one here before, yeah, you would always need to rotate the antenna at your base station in the same orientation as the balloon to get a good reception. So you don't need to do this here because the field rotates by itself. And so this is also used for satellite television, for example. Because if you can have it right turning, you can also have it left turning. And so you can transmit two stations, two signals at the very same frequency. That's the idea there. Okay. And yeah, so these are the two videos here. I think this one is also linked there. There is also some GeoGebra applet where this comes from, where someone has simulated this in GeoGebra. And this is the circular polarized wave that we had just had a look at. So yeah, instead of the video, you can also have a simple plot as a function of time for different places. So there's a phase shift, or for one instant of time for different positions, there's a phase shift. But at the end, it's such kind of wave. This is what we have just seen in the video. And yeah, so now the idea is, if you, let's draw some schematic, and let's use a new page. So if you have a plane wave going in this direction, and you have some metallic surface. And so what will happen is the wave will be reflected. And the reflection will happen in a way that, if this is a conducting metallic surface, that the field strength tangential to this metallic surface will be very small, or will be zero, because the metallic surface will short circuit the field. So if you have a wave coming in this direction, it will be reflected, it will travel in the opposite direction, and you will get, as a superposition of a traveling wave in one direction and a traveling wave in the opposite direction, you will get a standing wave. And a standing wave pattern might, for example, look like this, that you get, now at the end, of course, I should have the same half wavelengths here, but that we have some zero here, some field node here, and some field node here, and some field node there. And so now, if I would introduce a second wall at this position, no problem, there's already a field zero, there's already a null. So now if I would continue this, and if I would have fields, let's say, propagating like this, so a wave traveling like this, it would be reflected, it would be reflected, it would be re-reflected. And so I could propagate fields with this. And what I've built now is a waveguide. Something that is very efficient in propagating electromagnetic energy at high frequencies. And so this is how it looks like in practice. I think this is some something from a Russian. If I would zoom in, I think there is also, does anyone of you can read Cyrillic letters? So I can a little bit. So this, but I'm not sure what it means. So this is vchot. I'm not sure if it's input or output because the names are very similar. But I think this is like input. I'm not sure. Maybe it's also output. So there's a matchbox for size comparison. And so this is the waveguide system as set off some Russian fighter airplane for the radar system. So you have magnetrons that would be connected there to generate electromagnetic waves, and you have antennas connected somewhere, and this waveguide system propagates these waves. And so the next idea is, okay, if we have another wall here, and if our plane wave would continue, it would be reflected, and it would be reflected, and it would be re-reflected, and re-reflected, and re-reflected, and re-reflected, and so on. If we would have another wall here, then we would have built a cavity resonator. And a cavity resonator, you all have a cavity resonator at home. You call it microwave oven, right? And so this is a modern one. This is one of the first microwave ovens that has been developed, and it was sold by a company called Raytheon in the 1950s. And this Raytheon company was also a company that developed radar systems, for example, for aircraft, after and already during and after the Second World War. And let's say from the unknown heroes of everyday life, this is the person who invented it, Percy Spencer. And he worked for this company, and he worked with magnetrons, with let's say the sources within these radar systems. And so the legend says that he was in his lab, and there was a magnetron on the table working and somehow radiating, and he was standing in front of the table. And then he suddenly felt a warm, nice sensation in his trousers. And what happened is that he had a chocolate bar there, and the chocolate bar would melt. And so he thought, okay, this with the electromagnetic waves, maybe we can not only use it for radar systems, maybe we can also use it to heat up food. So he did some experiments, and so this is also what you can try out. If you take corn and put it inside the microwave oven, it will heat up, and the water will evaporate, and the solid hull cannot hold the pressure anymore, and then it will turn into popcorn. You can also do something. You can do some experiment. You take an uncooked chicken egg, put it into a microwave oven. The same happens. So you should only do this if you have the maniac need to clean something, because what will happen is called an explosion, and it will look like this. Luckily, I could find a picture like this on the internet. I did not need to do this myself. And so the field in the microwave oven also looks like this. So we have the metallic walls around. Field strength will be 0, or at least the electric field strength, the tangential electric field strength will be 0. And then we have these antinodes of the standing waves where the field would oscillate a lot, and where you have high field strength, and where the food would heat up very quickly and burn. And you have all these lines where the antinodes, where there's no field strength at all, where there's no power, where the food would stay cold. And so, now the food that you put in there contains water. Water has dielectric molecules because of the oxygen and hydrogen. And so they would like to oscillate with the field. And so there would be friction between the water molecules, and they will heat up your food. And so the problem is food would heat up at some positions very quickly, and at other positions it will stay cold. So what does your microwave oven manufacturer do to make the food evenly hot? There's a turntable in there. And so the purpose of the turntable is to move the field through this standing wave pattern so that it gets evenly hot and will not be burned at some of the positions. So still, people then don't know how a microwave oven works. Put the food just in the center of the turntable, so that it somehow rotates but does not really change position. So if you know how microwave oven works, the idea is to put the food on the, let's say, on the perimeter, on the outside of this turntable, that it really moves through this field pattern. Okay, so then a typical question is it okay to put a metal pot, for example, in the microwave oven? What would you say? No good idea, because it's made out of metal. It will also reflect the field. The field will not get to the food. The food will stay cold. And the worst thing happening is that the field will be reflected back and will also be reflected back to the magnetron. And so instead that the magnetron will heat up the food, it will heat up itself and it will potentially be destroyed. So a pot in the microwave oven is not a good idea. What is with a spoon? Spoon is perfectly working nice. I do it all the time because there will be some induced currents on the spoon, but the fields can get to the tea. The tea will get hot. The spoon will get hot as well, but no problem. So this is somehow okay. If you have a fork is not a good idea, because the fork has these tips, and at the tips you will get enhancements of the field strength, and you might get sparks and spark overs. So this is okay, but in general, don't put metal in a microwave oven. Is true. Like for CD, there's also a very thin metallic layer that cannot carry the current, and that will burn. And the same as if you have tables, let's say with some gold plating, then they will also be typically destroyed. So don't put metal in a microwave oven. You can also use your microwave oven at home to measure the aforementioned velocity of light. You take a chocolate bar, you remove, of course, the aluminum foil around it, and you put the chocolate bar in a way in the microwave oven that you somehow disable the turntable so that it stays at a fixed position. And what will happen, as said, is that the chocolate will melt and burn at some positions, for example, here and there. And in other positions, it will stay cold. And so now we can say, okay, there must have been a maximum here and a maximum of the field strength here and a maximum of the field strength here. And the difference from one maximum or from one burn spot over the next burn spot to the next burn spot, you can take a ruler and measure, and it's approximately 12 centimeters. And so with this and the frequency of the microwave oven, and you find this on the plate on the back side. It's 2.4 gigahertz or 2450 megahertz. And it's the same as Wi-Fi. It's the same as Bluetooth, because it's some ISM band and this industrial, scientific, medical, where people are allowed to radiate a certain amount of power. And so now you can calculate speed of light, velocity of light, by multiplying wavelengths with the frequency, and then you nicely end up with something like the 300,000 kilometers per second with a measurement that you can do at your home.